Hello. This is going to be a very, very quick lesson on a wing and how a wing produces lift. Um, it would appear if you go online and look up arguments about flight and the idea of how an aerofoil or a wing produces lift, there's a lot of people that will say that this is a mystery and that the production of lift via a wing is something that's an enigma and has never been fully understood. That is essentially not really true. It's a fallacy. We have a great deal of knowledge about how lift is produced, and engineers, aerodynamic engineers, aeronautical engineers, are able to calculate exactly how an aerofoil will behave in most instances now. The problem, of course, is that the equations in the situation, when you're dealing with a fluid rather than solid objects, the physics becomes quite complex. And so if you want an intuitively well understood explanation that can be explained to a layman like myself and yourselves, it becomes exceedingly difficult. There's a series of formulas that are called the Navier-Stokes formulas, and they do a great job of explaining how a wing produces lift and predicting how it will behave. Unfortunately, those formulas, you would need to be studying an undergraduate program for quite a while to have a full understanding, and you'd have to have very good levels of mathematics. So to explain lift in a way that's easily understood is quite difficult. Now, I thought that I understood how a wing produces lift because I did, when I was doing my pilot's license, we did a thing called basic aeronautical knowledge, and we discussed how a wing produces lift. And they were using the Bernoulli principle, which we've studied. And so they used that Bernoulli principle to explain how an aerofoil produces lift. And it was a great explanation that made a lot of sense and was easy to explain. And you thought, well, there, I understand how a wing produces lift. Unfortunately, if you ask enough questions about the explanation starts to indicate that it's not really an adequate explanation of how an aerofoil works. And it's based on the idea of what's known as equal transit. So I'll explain this principle. It's one that's accepted for the HSC as how a wing produces lift. So if they ask you how a wing produces lift, you can produce this as an answer. It's part ways towards an answer. It's partially true, but it also has some problems. So we'll do the Bernoulli equal transit idea first. So if we were to look at a wing cross section in a traditional sense, it's normally that shape. Now, can we see that? Yes, we can. So we've got this camber over the top and a flat bottom, okay? Now, you can draw a chord through the center. That's the chord that divides the wing up in half. And that's called the chord of the wing. Now, when your air is flowing over the wing, if the wing is moving in this direction, we'll have a flow of air over the wing. And in the traditional explanation, your airflow is all parallel. So under the bottom surface of the wing, it'll just keep going. But when a piece of airflow hits the top of the wing, it has to go over the top. Over the top. So, in the traditional explanation, they say, using Bernoulli's principle, we know that total pressure, this is just in words, so let's write Bernoulli principle. We say for the Bernoulli principle that total pressure is equal to static pressure plus the dynamic pressure. And this total pressure over here for the given system is a constant. So if this goes up, because it's the sum of these two, the other one has to go down. If this goes up, that one has to go down. Now, dynamic pressure is how fast the fluid is moving. Okay, so we know from the Bernoulli principle and also the effect called the Venturi effect that if you have a fluid flowing through a Venturi, which means you've got a wide bit of pipe that narrows like that, as it travels into that narrow part, it speeds up. Okay, so when it speeds up in this part here, the dynamic pressure goes up, so the static pressure goes down. So what does that tell you? That tells you that if a fluid is flowing faster, its static pressure is lower because it's dynamic pressure. Dynamic, think dynamic is movement. Okay, so as this goes up, the static pressure has to go down. So what they would say in the equal transit argument for lift is that if we have our air particle arriving at this point here at the top and at the bottom, so we've got two little particles of air, by the time they get to this point here, okay, this top particle has to go over this hump. Okay, it's traveling a longer distance because it's not traveling straight. So for them to both arrive at the same point here, the top particle has to travel faster. And we know from our Bernoulli principle that if we have a higher dynamic pressure, because the particle's traveling faster over the top of the wing, we'll have lower pressure on the top than on the bottom. So that means that our pressure on the bottom, static pressure on the bottom, static pressure here, is greater than the top. And on the top, static pressure is less than bottom. So basically, the Bernoulli principle is telling you that slower air has a higher static pressure. So, and we know this wing, if it's traveling and it wants to produce lift, it's going to be going up, isn't it? So we're going to have higher pressure here and lower pressure here, okay? And it's going to go up. What's wrong with that idea? Okay, what is wrong with that idea? Now, I looked at this explanation when I was taught it and I thought, great, I understand lift. But I didn't understand it fully, because one of the problems with this explanation is that they say that these two particles arrive at the same time. What law in physics says that the two particles have to arrive at the same time? There is no law. But yet the wing still produces this lift. So you would think, well, that's indicating that that's actually true. What actually happens, and I'm going to give you a video below this one to show you in a wind tunnel, is this: if you have particles top and bottom, or wind flow top and bottom, that this is flowing way faster on the top than the bottom. So it's actually faster. If you just had equal transit, it probably wouldn't produce, it would produce a difference in static pressure, but it wouldn't be enough to explain the amount of lift that a wing produces. So it actually gets here, in actual fact, if this one gets here at this point time here, if they arrive at the same time, the other particle might be somewhere here on the wing. Okay, and when I show you the video, you'll see that that's actually the case. So we do have faster flow over the top than the bottom. So you might be saying, all right, equal transit doesn't work, but that's what's happening, okay? But the other problem with this explanation is, if you were to look at the Wright brothers aircraft, it didn't have a curved wing. It had a flat wing, and it still produced lift, okay? And I'm sure that some of you have seen planes doing this, flying along, and then they do this. Do they crash into the ground? No, they still keep going, upside down, producing lift. So this theory that utilizes the fact that this top surface is curved and that it has to travel further doesn't really explain it. But for your HSC examination, they're happy to take that as an explanation because it is part way towards the answer. Okay, so that is the Bernoulli principle, and I'm going to put in brackets underneath equal transit explanation. Okay, so I might just write it up here actually. So if you want to explain the lift, you can use the Bernoulli principle equal transit argument. Now, if you wanted to make this argument a little bit more convincing, you could just start by saying in a wing that produces lift, the airflow over the top is faster than the airflow along the bottom. Okay, and that will get you a ways towards explaining lift. Okay, now this explanation was used for many years, and it still appears in textbooks. But there's actually an explanation using Newton's laws, which is called the turning force explanation using Newton's laws, and it's airflow turning. So the airflow actually has to turn. So we'll talk about that in the next video. So you'll have both arguments.